Right, 11 o'clock, so we start on time, punctually. Just to make everybody aware, this meeting is recorded right from the beginning in case you didn't get the message. Welcome to our iGGi seminar series. This is the first one, so we're all really quite excited. We have a panel of 5 people today. One is special, but I will come to that in a little bit. So we're starting off with a very, very interesting topic, which is how can a computer learn in a world too vast to explore completely? Very philosophical topic, maybe. A little bit about the format of these series. So we envisage that we have 1 to 3 guest speakers from industry or senior research, and 2 iGGi students with matching research interest. And basically everybody gets a short space of time for a pitch, and then there will be a panel discussion on a predefined topic. So as I said, today's topic is how can a computer learn in a world too vast to explore? And I shall introduce our panelists today. I'm starting with Guy Davidson, who isn't strictly speaking an expert on machine learning, but he said he might join from an industry perspective, might join future panels as a bit of a regular. So we thought that he and I could be sort of co-hosts, a bit like an Ant and Dec sort of style, or I'm not sure what did you suggest, Guy?
I'm thinking Montague, actually, but you know.
You weren't happy with Ant and Dec. Oh yes, that's true. Binder and Davidson does have a ring, doesn't it? I suppose. So maybe can I lead on to, oh, sorry, whoever doesn't know me. So I'm the iGGi manager for the QMUL site. I've started my role in March this year, but I'm also, my role is also outwards facing in terms of making contact and establishing, fostering links that we have with industry and senior research in the games industry. Guy, over to you.
Hello, my name's Guy Davidson. I'm the head of engineering practice at Creative Assembly, which is the UK's oldest and largest game studio. Well, largest at the moment, but will continue to be the oldest for a long time, I hope. My role is actually the development of engineers. I also have outreach role, particularly specialising in diversity and inclusion. You may have heard of the inclusion group #Include, which I started 4 years ago. This is a community of about 8,000 engineers who are all learning C++, who are C++ practitioners. It's a moderated chat server that abides by a code of conduct derived from the Berlin Code of Conduct. One of the biggest problems we have in engineering at the moment is we have so many problems to solve. We have insufficient engineers to solve them. The representation of engineers by gender, by ethnicity is appallingly skewed and does not include a very large representation from society as a whole. So that's my main concern at the moment outside of Creative Assembly, is trying to recruit people from more backgrounds to solve some of the very real problems we have in the world today.
Okay, so yeah, having said that, it was noted that today's panel is an all males panel, and we have a thing or two from iGGi to say about that. First of all, it doesn't really fairly represent the breadth and diversity that's already present at iGGi from the student side. So it was coincidental, really, and we will really definitely strive in future to better represent our diversity that's actually already existing. So hopefully that will be a one-off, but obviously also equality isn't just about gender equality, it's about a lot of other aspects, and we generally strive, it's our attitude to strive for this diversity, and yeah, that's just to be highlighted up front. But now let's focus on the actual subject of the debate, and I'm leading on to Tom Schaul from DeepMind, who actually proposed the topic. So Tom, over to you.
Yes, hello. My name is Tom Schaul. I'm a couple of words about me. I'm originally from Luxembourg. And then I went abroad because Luxembourg is very, very, very small. So we all have to leave the place. I went abroad to Switzerland and the United States to study with the machine learners. Among you might know my advisors, Jürgen Schmidhuber and Jan Lecker. Then in 2013, I came back to Europe, to London, to participate in this little startup at the time called DeepMind, which is a little bit bigger by now. I've been at DeepMind now 8 years, working on a whole range of research topics because there's a lot of cool things going on, and I tend to be excited by many different directions, easily distracted. But there's kind of a core theme, which is reinforcement learning, learning from experience, learning by doing, having our agents act in the world and learn from that experience. And in that context, I've been working mostly with games. So I think there's a lot of resonance with the iGGi program here, trying to figure out how to make games the best training grounds, the best test environments for AI and machine learning. Concretely, like one of the biggest projects I've been involved was this thing a couple of years ago on StarCraft 2, where we tried to build an agent that could learn not quite from scratch, but almost from scratch how to play StarCraft 2 at expert level, grandmaster level. And we faced many challenges, and one of these challenges is been a long time concern and kind of nagging issue, is this issue around exploration, around how to best act, how to best generate your own behavior. You have this very empowered computer system that doesn't just get to learn whatever it wants, but it gets to act in some interesting environment, the way it wants to collect the data it wants to collect. You don't pre-feed it the data, you don't give it labels, you don't tell it what kind of specific things to do. So if it can explore in a rich and interesting and vast world, then how should it do so in order to make learning effective? And is it even conceivable that we could build such machines? And so I think that's the overall theme. I have more things to say about the theme as things come up, but I kind of just want to highlight that this is hopefully a very relatable and kind of ubiquitous thing. It's like like almost all of the interesting problems that we are faced with are vast worlds. Like there's of course there's tiny, constrained, clear problems where we can find the optimal solution and solve something perfectly. But almost all of the interesting things that we are faced with, that we would want to apply to AI are vast. We can never cover everything. We can never try all possible ways of driving a car. We can never try all possible ways of building a rocket. We can just try a few. So the world is always vast. And if they are vast, we have to learn, right? We can't hope for some kind of mathematically derived optimal answer to these things. And so learning in vast worlds is the bread and butter of AI, I think. And so I think a lot of the questions that come up in all kinds of contexts will have some exploration and some resonance to how to collect data in these kinds of settings.
Okay, great, thank you. Over to, I think we settled for alphabetic order by first name. So Adam Katona, who is a year 3 iGGi student.
Yeah, thank you. My research is about evolutionary computation, not reinforcement learning, but I am also trying to solve the same kind of problems which are typically attempted to solve with reinforcement learning. And Tom mentioned that he is interested in whether is it conceivable for such a system to build such a system which explore such vast worlds. And I'm very excited about evolution because we don't have to conceive it, because it's already demonstrated that evolution is able to explore such large worlds and evolve human intelligence. So I prepared some notes for this introduction. So basically, I have two angles to approach this topic from an evolutionary perspective. One is about how to automatically generate stepping stones or curriculum via open-ended evolution for learning, and the other is how can we discover good exploration strategies with evolution of evolvability, and what can the two fields, how can the two fields learn from each other. So about open-ended evolution is what we call open-ended evolution is when a system seemingly endlessly generates interesting artifacts, like in natural evolution. Maybe not for the first few billion years, but once evolution started, it created immense amount of diversity and of strategies and organisms. And why this is important is because this diversity is a stepping stone for further learning. So by creating new strategies, new niches become available to explore, and this automatically generates a curriculum for learning. So one researcher who really demonstrated this point is Kenneth Stanley, who created this system called Pig Breeder, where humans can evolve images by selecting from, like, mutating a parent image and selecting their children. And what he found is that it's basically impossible to evolve something if you're looking for it. If your objective is, for example, to evolve a car, it's really difficult, and he couldn't do it. But when people evolved different things, unrelated things, and suddenly someone thought, oh, this looks like a car, and they could evolve a car. So by generating all these stepping stones, by discovering all these divergent strategies, you could evolve all kinds of objectives. But if you are looking for it, you cannot. So I think this is something that is very important for exploration. So the other aspect where evolutionary computation intersects with deep learning is that our current deep learning approaches use direct encoding, where all the learned parameters are mapped one-to-one to how the network is represented. So for example, each weight of a neural network is learned directly. This is a separate parameter. While in indirect encoding, we have some genetic code, and this genetic code goes through a complex transformation, the developmental process, which creates a representation, like it creates a brain. And what this allows is for evolution to turn random noise in the genotypic code into a very specific variation in the phenotypic. So like random mutations in DNA can create very specific changes in the organism or the brain. For example, in the case of a fruit fly, you can, with a single mutation, you can change the fly to have a antennae, a leg grow instead of antennae, or have 4 wings instead of 2. So this kind of developmental encoding, which is unique to evolution, allows the automatic discovery of this modular and symmetric representation. And this allows a new kind of learning, which is not possible currently in our deep learning systems. I think this is this also can be really important to automatically discover exploration strategies. Yeah, and that was my introductions.
Okay. Great. Over to Alex Whittaker, who is Fusebox Games. Is that correct,
Yep.
Alex?
Morning, folks.
Yeah, so he is our second or third industry representative.
So briefly about me, I'm also the chair of the iGGi advisory board, and I've been in the games industry for, well, I don't know, since the last century anyway. In my time, I've always focused on AI. In fact, I worked with Demis Hassabis, Tom's boss, on his second game, Revolution. I did the AI for that. So, but yeah, I've hopped around in various different areas. I've mostly been focused, I'd say, more on sort of symbolic logic and behavioral logic would be my area. But my thesis was actually in genetic algorithms. I wanted to just start off by talking briefly about how the kind of first step of a learning system would be to kind of perceive the world and convert that series of inputs into some kind of semantic representation. It's a little bit like the tokenization step of parsing. You need to first of all build a kind of more semantic, meaningful model of the world, which you would then potentially use to train some hill climbing algorithm to infer a next state from a current state. That's possibly a simplistic way of looking at it, but broadly speaking, that's what we're hoping to achieve with our learning system. If we think about the world, this vast world, as actually being the world as represented in computer games, for instance, then obviously that step is a little bit easier because generally speaking, the computer game representation is already made up of tokens. There are logical units which have got associated with them, various different tags. And so we can kind of elide that step of semantic inference to a degree. So I think it's worth noting that there is a huge space that hill climbing will help with in the real world in terms of doing that initial edge detection, recognizing objects within the world, or from vision or from sound or whatever. But we can sort of skip that step and get to the next piece, which is to try and infer some kind of sense from those objects, to infer a state and predict what a transition into the next state might look like. So one of the other advantages of having a virtual world is that obviously it's very easy for us to build up a large test set as well. So if we think of our virtual world as being something like No Man's Sky, for instance, then our virtual world is infinite, effectively infinite, and is constrained by a set of rules that are used to generate this procedural experience. We can tag those into some kind of semantic picture and then train an agent to recognize state and predict the next state. Why would we want to do that in a game when we could write a behavioral system to do that sort of thing? Well, the process of learning is interesting in itself. So I think actually being alongside an agent that is learning or exploring its environment and becoming more intelligent is exciting. The second aspect of that, of course, is that a large amount of state change is driven by the players who are interacting with that world. So, having an intelligence that is able to see what the players are doing and anticipate what they're going to do next, that could be pre-trained from a large number of users, or it could be learning as you are playing. That's an exciting and interesting thing to have to sit alongside you. So I think that's a space where I'm really interested to explore in this discussion and to think about a little bit more. I know that it maybe subverts the goal of a vast world, but I'm interested in game worlds. So I'll leave it there and hand over to our next speaker.
Thanks, Alex.
Michelangelo Conserva, sorry, and iGGi, year 1 student.
Yeah, I'm gonna share my screen. So I'm gonna present my point of view, which is Bayesian. And so we're talking about randomized exploration. I want to start my quick introduction with a quotation which has been attributed to Harry Klopp. So it says, other learning paradigms are about minimization. Reinforcement learning is about maximization. At first sight, it may look like a tautology, but it actually reveals an important element of distinction of reinforcement learning. Typically, learning paradigms such as supervised learning and inferential statistics, they all aim at learn, in some sense, observe patterns and phenomena. So they aim at minimizing the difference between the model and the data. This is not the case for reinforcement learning, as it is distinguished by this open-ended view and the pursuit of the unknown. A reinforcement learning agent learns to improve its behavior over time without a prescription for eventual dynamics, the limit of the performance, or even the time horizon sometimes. And this leads us to the concept of sample efficiency, which is closely related to exploration. In fact, with sample efficiency, we mean to solve an environment, or maybe to find a strategy to win a game with the minimal amount of interaction as possible. So this means to explore the world efficiently. And the problem is, how can we design a sample efficient agent? Well, that's a very hard question. But what we can do is to carefully design the agent with sample efficiency in mind. And here we are at the core principle to design sample efficient agents. And we're going to analyze them with a very simple example. So imagine that you have to design an agent with the task of finding the brightest star in the sky. Clearly, to seek relevant information for the task, the agent should go out in the night, preferably in an open field far from the bright cities. However, it is also important that the agent brings a telescope with it, not, for example, a magnifying glass. The telescope, in fact, enables the agent to look in the sky efficiently. Finally, when the agent goes back home early in the morning, it should write down about the position and the brightness of the star itself, and not maybe about how bumpy the country road is or how scary the forest is at night. And these are the principles to preserve sample efficiency. And so these are the guidelines to define exploration strategy. You can now see the typical routine of this learning-based agent. So while interacting with the environment, the agent collects data, which is used to derive an approximate knowledge of the environment. And this knowledge can be encoded in many different forms, as for neural networks or with tables. So it's very different. And the main point is that this knowledge is used to improve the current policy of the agent. And in turn, it should hopefully improve the quality of the data the agent will gather. This is the crucial step. So the policy improvement step. It is crucial for sample efficiency because, for example, if the agent repeatedly visits a part of the environment space that is already known and it's not optimal, then the agent will waste a lot of time and samples on it. Instead, what the agent should do is to direct its exploration strategy to part of the environment which it is uncertain about. And when talking about uncertainty and how to handle it with statisticians, half of them will think of confidence intervals and the other half of Bayesian methods. In the reinforcement learning literature, the frequentists, so the one concerned with the confidence interval, have developed optimistic exploration strategies, whereas Bayesian studies randomized exploration strategy. And as I lean toward Bayesian thinking, today we're going to talk more about Bayesian methods. And from a high-level point of view, being Bayesian means to encode everything you're uncertain about with probability distribution, and then update this distribution as you gather more data. These allow you to leverage extremely powerful tools that unfortunately comes with a cost. The main strength of Bayesian methods is that they allow the agent to explicitly and optimally handle the exploration-exploitation trade-off. So in a few words, the agent can direct its exploration with the purpose of decreasing its uncertainty about the environment. And this procedure can be made extremely rigorous as Bayesian agents encode their uncertainty through probability distribution. Just to make an example, Thompson sampling, which is a randomized exploration strategy, and Thompson sampling agent at the start of the episode or the game sample from this distribution and that act optimally with respect to such samples. Finally, it's also very important that the agent designer can typically encode prior knowledge through prior distribution in Bayesian agent. And the prior distribution are which that come before this agent start interacting with the environment. So they encode the initial belief. Even though the use of prior distribution is of significant importance for Bayesian, it doesn't work very well with deep learning method with the current methodology. So this is not available. Further, Bayesian inference is very computationally intractable for complex scenario. So it is necessary to recur to approximate inference methods such as variational inference of bootstrapping. And neither this technique combined with deep learning is extremely well, even though there has been some progress in the past 5 years. And finally, there is a subtle but quite complex problem, which is the violation of the iID assumption when using bootstrapping reinforcement learning. But this is a complex topic that maybe we can discuss later on. I end my quick talk with some reference if you are interested in getting more Bayesian. So thank you very much. This is all for me.
Thank you very much, Michelangelo. Right, well, this is a seminar, so we'd like to throw it open to the floor. There are two ways that you can ask questions. You can either raise your hand, which you'll find in the reactions at the bottom of your Zoom client, or you can type questions in the chat. Whilst you're all thinking of your questions, I've got a question which I want to direct to Alex. You mentioned that you did your original thesis in genetic algorithms. It's quite a while ago. I studied GA at university back in the 80s at Sussex. I wondered, I haven't been following AI as closely as you, I suspect, and I wondered if you could, how much has the world of AI changed over the past 10, 20, 30, well, 40 years?
Well, I studied AI at Queen Mary at master's level, and in I think it was about 88 or 87 or something like that. At the time, I think quite a lot was a lot of focus on multi-agent systems. That was a really sort of interesting area, and I think the idea, especially the excitement with distributed computing, agoric systems, that kind of thing, was very of the moment. In fact, I think there was some talk of setting up a multi-agent systems kind of center at Queen Mary at the time. There was also still quite a lot of discussion between the kind of that kind of Rod Brooks kind of world of behavioral AI versus the kind of representational kind of systems, all intelligence is search or something like that. I don't recall what was something along those lines. I think we've moved a long way since then. At that time, I think neural networks were the kind of things that would be used to just recognize images, like hot field networks, or they would, they were occasionally in the news as being trained to, I don't know, recognize decent wine from not very good wine, that kind of thing. So we've moved a hell of a long way since then. I think a big impact on that has been kind of cloud computing and large scale compute, which has really helped a lot, and certainly has shifted the dial on learning. I think it's a shame that we've kind of moved away a lot from the kind of more representational thinking, planning, that kind of thing, because I think that there is still something to be learned there, and I do wonder if there is, a real step forward might come from some real strong hybrid between those two ideas.
Excellent. Thank you. So, would anybody like to ask a question?
I think students had some questions already prepared, so maybe if we can jump to those.
Well, we have a question from, we have a hand from D. Hernandez. I'm afraid I don't know who you are. Could you introduce yourself to the panel?
Hello.
And then ask your question? Thank you.
Well, I'm Daniel Hernandez. I'm a fourth-year PG student. However, I do wanted to say that if there are some written questions, I can lower my hand and wait my turn dutifully. But I have no qualms with that.
No, I'll take hands first, please.
Oh,
carry on.
Okay, so I wanted to ask a question to Tom Schaul. So, especially without trying to antagonize you against Adam, because you're more reinforcement learning focused and Adam is more evolutionary minded. So I think that one of the big benefits, so I'm a reinforcement learning person myself, so maybe I'm not phrasing this properly, but I do think that one of the benefits that evolutionary algorithms have over many of the other approaches for generating game-playing agents is that you're inherently working with a population, which means that you have this inherent capacity of exploration just by virtue of maybe having different parameterizations which are acting themselves on the environment. And sure, one could argue that with reinforcement learning, especially with more advanced algorithms like Impala, where you do have multiple agents gathering resources to potentially multiple learners, that you can still mimic this sort of distributed behavior, let's call it. So I wanted to ask, with your extensive experience on reinforcement learning, what do you think that could be, are there things from evolutionary computation that we're missing? Because in reinforcement learning, we're mostly focusing about this one agent that is acting on the environment, and of course that drives this like local optima that you may start cycling through, but without getting to the cycle multi-agent aspect of it. Is there any sort of low-hanging fruits when it comes to exploration that we could be learning from other things like evolutionary algorithms that we're just missing out completely?
Excellent question, thank you. Panelists, if you've got anything to contribute, unmute your microphones and I'll run through you in order. Let's start with Tom.
Yeah, I think the question was aimed in my direction, so let me start on this one. Yeah, thanks for the question. I think this is an excellent point to maybe clarify something, at least how I see reinforcement learning really is as a class of problems. The class of problems where there is a clear scalar reward signal, a goal that is unambiguously defined, and you interact with the world by acting, by collecting experience in order to maximize this signal. That's the reinforcement learning problem. You try to learn how to produce a lot of reward. And then in terms of solution methods, there is a conflation because there's a few very standard like DQN or temporal difference learning or Q learning or these like very classic approaches that people say, oh, reinforcement learning is Q learning. But reinforcement learning as a problem is very broad and it kind of includes, you could do evolutionary algorithms as the solution to a reinforcement learning problem as well. So I think just to distinguish that. But then I agree on the solution side, the things we typically do suffer from there's two big differences, and you highlighted them one a bit more than the other. One difference is that the single agent idea makes you think that there's one point that's moving. You're moving the parameters of one network, or you're moving one piece of knowledge that's kind of moving through space by experiencing. You have one body or something like that. This is the first thought that comes to mind when you do reinforcement learning. And then the population view, which gives you lots of extra power, as you described, is maybe necessary, especially if the world is vast, especially if you want to learn really interesting things. You may actually want to have massively parallel experiences, and you can do that. I mean, Impala is an example. AlphaStar, the StarCraft agent we built, also collected experience through hundreds of different agents that all were subtly different and were all showing slightly different rewards and goals, and collected all of the experience together to produce the best behavior in the end. So the parallelism is definitely a superpower that we should give our agents if we can. The other one is the other big difference between the classical reinforcement learning solutions and evolution is the local versus non-local search. Like most people in RL do gradient-based methods. So the gradient-based method means that you are at this point and you look at the locally best direction of improvement. So you take small steps that are informed by some kind of gradient on which way is it going uphill. Whereas evolution tends to do much more disruptive, much bigger mutations. It doesn't try to grow one of the wings of the fly a little bit. It just makes a mutation and bang, there's two new wings in a single step. And that's something that gradient-based methods can never do. And so there's a complementarity. Some parts of the problem space are much better tackled with careful local movement, tuning your solution, gradually improving, gradually honing a certain skill and getting slightly better each time you try, versus jumping and trying something radically new. We do want to embrace both. And you're absolutely right that the jumpy version, the evolutionary version, is harder to do, I think. And it has been done less, but it's just as necessary as the local improvement steps in the long run.
Thank you, Tom. Adam.
Yeah, so I have a few points. So first, about what is reinforcement learning, and Tom said that reinforcement learning have like a clearly defined goal. And yeah, I agree, I can formulate the problem like this, but sometimes if you want to solve a goal, it's maybe more difficult if you are searching for it than if you are exploring freely. So the kind of how evolution differs from reinforcement learning, even if it's applied for reinforcement learning problems, is that evolution tends to, or at least some kind of evolution, a kind of which is encouraged to do open-ended search, is a divergent. It's doing divergent search. So it's not. It doesn't have a fixed goal. For example, in nature, evolution is to only have like a minimal criteria for reproduction, and if you pass that, you can reproduce. And there are so many ways to so many strategies which which fulfills this criteria. Yeah, so I think that's one difference between evolution and reinforcement learning. Yeah.
Thank you, Adam. And Alex.
I wanted. I'll only speak briefly on this because it's not an area that I've been working on recently. But one of the things I touched on in my thesis was that the idea, once you have an algorithm that is effectively representing how your evolution is going to work, you've got obviously you've got a fitness function, but you've also got a function which is going to determine what your next generation is going to look like. You don't have to stick to a kind of classic experience of how we understand genes to work right now. And I proposed the idea, and this is when I say proposed, this is in the loosest sense. This is only an MSc thesis, so it's not. There was no paper or anything. But the idea of a kind of Lamarckian inheritance. So what you would have is that the organisms behavior would be representative of their genetics, but through time they might tune that behavior through their lifetime experience, which would effectively be a small amount of learning, and then what they would pass on to their next generation would be the tuned version of their genes rather than the underlying version of their genes. So you end up with, I called it Lamarckian because you can imagine Lamarck thought that giraffes stretched for leaves and then their necks grew longer and they passed those longer necks on to their offspring, rather than in fact it was slightly more complex than that. Short-necked giraffes went hungry effectively. So I guess what I'm saying is that because in a genetic algorithm you are not bound by how we understand genetics to work in life forms, you can explore the space much more and in fact find new ways of evolving, which could be quite exciting, and allow your hill climbing algorithm to occasionally leapfrog effectively. So it becomes maybe a little more like simulated kneeling or something like that. You're kind of climbing, and then jumping and then climbing a little more. That was my comment.
Thank you, Alex. Susanne.
I haven't got a great deal to say on this. I'm
a
co-moderator.
I'm throwing to you as if we were on television.
I would like to suggest that we maybe take it in turns to take questions from panelists. I think our students definitely had some questions prepared as well, and then take questions from the audience. I'm slightly in favor of audience typing questions in the chat so that we can assess the questions a little bit beforehand. I see that Francesco has a raised hand, so I don't know if it's possible for you to maybe type your question before we take it. And maybe Michelangelo hasn't spoken, so maybe Michelangelo, I think you had a few questions already prepared if you want to maybe ask one or two.
I actually have my point for this last question.
Yes, go ahead, please.
Yeah, because the idea of population exploration is very interesting. And this actually combines very well with Bayesian methods, in the sense that with Bayesian agent, you can have a centralized agent that is called the learner. So the learner is in charge of learning the parameters, the policy. And this learner, since it's a Bayesian learner, can sample agent, or more correctly, actors. So you have a centralized learner, which has a set of probability distribution over policies, and then you can sample from this distribution. And so you can sample many different actors, and you can use these actors in parallels to gather experience. So you can have like 100 parallel experiments with 100 samples from the probability distribution of the over the agent policy. So this is a very high level concept, but more or less a Bayesian method can be implemented in such a way. And this is exactly what Thompson sampling is. This is this randomization strategy in which you sample the actors, you gather experience, and you update the probabilities distribution in the centralized learner. And yeah, this is my take on the point.
Great, thank you. Good answer. Did you have a question to the panel? Michelangelo, sorry.
Oh, no, I just wanted to add my point. Yeah.
Just last point.
That's fine. Adam can jump in.
Genetic algorithms also have like this transition between like probability distribution and like discrete population. For example, evolutionary strategies is like a hybrid between the two. So it's like using a probability distribution, like they represent the population as a probability distribution as well. So it's like really interesting how these hybrid algorithms can work.
Yeah.
Good point. Michelangelo, do you want to proceed with a question to the panel?
Maybe there are some questions in the chat.
Okay, you prefer those? That's fine.
Yeah, so far it's only been me replying to what you guys have said silently. And thank you so much for your answers.
Great, thank you. Maybe, so Francesco did have a raised hand. Yes. Francesco, did you want to present a question?
Yeah, sorry, I was typing it, but it's a bit long. So
that's okay.
Yeah, so again, I'm afraid it might exceed the scope. So if I do, just stop me, basically. So my question was more or less around the evolutionary approach and based around this paper that I read and I found very interesting from Jeff Clune in 2019 called iGGi, AI generating algorithms, an alternate paradigm for producing general artificial intelligence. And basically in this paper he identifies sort of 3 pillars, he calls them, to try to achieve this. And the first one is meta-learning architectures. The second one is meta-learning algorithms, which as far as I understand is more or less how the normal approach to this has been so far. But then he also adds a third, which is generating learning environments automatically. So basically creating an algorithm that creates a bunch of different environments so that the AIs then are trained in without those being created by the researchers. And this is an attempt, as Adam was saying, to amplify free learning, right? So since the environment consistently changes and poses different kinds of challenges, then the AI will have to adapt to that too. And I just wanted to know if this is sort of a common perspective or is this sort of a novel idea, if it's problematic, and what you think about it, more or less. Does it make sense, or should I clarify?
It makes sense to me. Shall we start? Which panelist would you like to answer first? Maybe you can pick.
Maybe Adam, because as far as I understand, he's about evolutionary-minded AI.
Yeah. Sure.
Yeah.
Adam.
So, yeah, this is really interesting because it also connects to these procedurally generated game words. So I'm generating environments with the goal in mind to make these environments the right amount of challenge so that learning can happen and skill building can happen. I think that's a really promising direction. And yeah, so there was this work called Poet where they did this, where they had a procedurally generated environments, and they tried to generate environments with the right amount of difficulty. And by doing this, it allowed the system to learn to traverse complex environments, which it couldn't learn by itself. So this automatic generation of curriculum, I think it's really powerful.
Okay, Alex?
Hi. Yeah, it's an interesting idea, especially if you want to sort of shake up the environment and create lots of test cases. I'm more interested though in turning that idea on its head. This is kind of from Dennett, the intentional stance, where he would say that a high-level organism is able to use mind tools to formulate a hypothesis and then test that hypothesis in the environment. So if you imagine that your genetic algorithm is able to recognize weak areas in its learning, to formulate questions that it might ask of the environment to test or strengthen those areas, and then to follow a behavior that allows that to happen, that would be more interesting to me. So provided that you've got, an example I posted to my fellow panelists was that imagine that your self-driving car comes across a chicken in the road and doesn't know what to do. Well, if you've got that experience from thousands of self-driving cars in driving across roads with chickens in, then that's fine, you can use that. But if it's a pretty rare environment, then what a really taking an intentional stance, what a hypothesis building vehicle might be able to do is to back away from the chicken first of all and see if the chicken follows it. You know, is the general behavior of chickens to follow cars, advance slowly towards it, see if the chicken backs away from it, is the behavior of chickens to avoid cars. And effectively, by building these hypotheses internally and formulating a plan to test them, it would be able to increase that space. Obviously, you'd hope that you're not in the vehicle that's investigating the chicken, but that would be a stronger approach than artificially generating random environments that strengthen your learning system.
Yep.
Great,
Thanks.
Tom.
So I guess the idea of curricula or changing the dynamics or the rules of the environment it's a very powerful tool. It's in kind of like most of us would, well, in the classical RL community, we would usually not allow ourselves to touch the environment. This is like usually treated as given as part of the problem definition. But if you can touch the environment, and specifically if you're not in the real world, where it's hard to change the laws of physics and say, let me try this without gravity. If you're in a game, you can say, oh, let me try this without gravity and see what happens. You can get really, really powerful generalization. You can get really powerful additional experience without fully breaking all of the causality of your environment. And there's been some really nice successes. So OpenAI had a paper where they built an agent that played Dota. And that was one of the key tricks that they used to do that. They basically accessed the game and changed all kinds of like health and spell effects and all kinds of dynamics, made certain things stronger, faster, more expensive, and so on in subtle ways to create, instead of a particular domain, a particular environment that is difficult, to create an entire space of similar ones, some of them that are harder, some of them that are easier, and then let the agent learn in that richer space where it always finds something to learn. And so this is if you have the affordance to change the environment and make it many related ones instead of just one, that's usually very, very beneficial. So I think it's a very powerful tool for these kinds of problems.
And Michelangelo?
Yeah, I agree with Tom, and this is not very applicable in many reinforcement learning cases. But as Alex was saying, one thing is that you can reason about hypotheses, and you can try to infer causal relationship. And it's interesting because there is a field that is called causal inference, and there have been some interaction with reinforcement learning. So there is this new mashup field called causal reinforcement learning, which is happening more or less right now. And it's a way to use causal inference tools to reason about what Alex was describing, which are the relation of the phenomenons. The main problem is that these models are very computationally expensive to run, and they need a very high level description. As Alex was saying, you need to know what behaviors the chicken can have, like the chicken can flee, the chicken can come, or the chicken can stay. In this case, we have reduced the behavior of the chicken in just 3 points. Whereas typically you observe the chicken, so you see an image, and maybe you can locate the chicken inside the space, and you need a level of abstraction that is a little bit higher, because you need to abstract from a simple chicken on the road to the behavior of the chicken on the road. So what kind of behaviors, like you have to abstract. And this is part of the representation learning that is part also of reinforcement learning, but it's not very simple to do.
Okay,
Yeah,
great. There's a comment from Eunice, then the car should feed the chicken. Just repeating this because the chat will not be in the recording part of it. Guy, over to you.
Okay, so John had his hand raised and he's very kindly typed the question into the chat. I'll read it out. I'm interested in the vast part of the topic. I'm unsure what the state of the art is in reinforcement learning, so apologies if these problems are largely solved. I am thinking about the inputs an agent has and how an agent explores a world which is vast in terms of the number of inputs provided. For example, the agent received images and audio, etc. What do the panelists see as the further for high input reinforcement learning, especially multimodal reinforcement learning? Within a game system, these inputs can often be handcrafted, but this may not generalize to the natural world. I expect that some sort of features extraction can be utilized, but these often have millions of parameters, especially considering something with textual inputs, which likely limits exploration. Do you see the future as a solely reinforcement learning problem, or do you expect some sort of pre-training, for example, self-supervised or supervised, would be required to avoid difficulties in learning with a large number of input parameters? How do not deep real learning models, reinforcement learning models, handle a large number of inputs? So any panelists want to take a stab at that? Alex.
So I think in my view, this touches partly on what I opened with, which is that you first of all, especially if there's a very large number of inputs, need to kind of dilute those down into some kind of tokenized view of the world, some semantic view of the world. And I think if the inputs are of a very, very wide type, then including text, for instance, which that's a big problem in itself, then I would imagine that you would need a large number of quite specialized and potentially very different systems for doing that kind of that initial feature extraction in the same way that human intelligence does, you know, different parts of the brain specialized in doing that feature extraction. I think that we tend to think of ourselves as reasoning from just facts, but actually, of course, a lot of our behavior is not fact-based at all. We don't cross a room by reasoning about the shape of the room. So the connection between all of those systems is not necessarily through one central point as well. It's entirely possible that some of these need to be wired directly either to each other or to the motor functions or acting functions of the agent as well. But yeah, I would imagine a layered and complex set of different feature recognizers before you can really get to something which a central intelligence that might think about that. But I wouldn't exclude the fact that those feature recognizers might communicate directly with each other and lead to actions, effects within that world immediately. This is something that's really interesting in the games world, and I know that, you know, it's a much bigger problem in a kind of real world, but actually, you know, maybe this touches more on general solvers rather than specific games systems. But I think it's something that that would add an awful lot of flavor to a great many games, even if it were just a kind of a passive assistant sitting alongside you that was able to kind of pick up and learn these sort of things.
Angelo.
I think that this is something that we can clarify, because this is something that slipped in when deep reinforcement learning came. So before there was reinforcement learning, and there was this kind of algorithms which were focused on these more or less specific reinforcement learning problem. And then deep reinforcement learning came. So they came with deep neural network for Q learning, and this was the first breakthrough. And in some sense, what happened is that they took images and they learned this Q function. So in some sense, what slipped inside the deep reinforcement learning is the feature representation learning. So you already do feature extraction representation learning while doing deep reinforcement learning. For example, there is a recent algorithm published by DeepMind, vector quantized planning. And in this paper, they use deterministic variational autoencoders to enable Monte Carlo tree search for stochastic and partially observable environment. But the main point of the paper is not in the use of the reinforcement learning algorithm, which can be regarded as the Monte Carlo tree search. But the main point of the paper is learning these deterministic latent spaces. So the main point of the paper is learning representation and then use it for reinforcement learning. You can do also a distinction, like you can do first feature learning and then reinforcement learning. And this is what happens in this specific paper, in this vector quantize for planning, something like that. And in which you first do training, you first train your variational autoencoder, and then you do reinforcement learning in which you learn value function, you perform Monte Carlo tree search. Or you can do like in mu0, end-to-end reinforcement learning in which you see an image and you output an action. So you can have end-to-end learning in which you learn the representation in such a way that is already good for reinforcement learning, or you can learn a compact representation and then use that for reinforcement learning. There are a lot of papers that do this. For example, there is an unsupervised methods for Atari, in which they first learn through unsupervised learning a compact representation of the Atari games, and then they use different reinforcement learning algorithms on it. So I think that this was one of the main points of deep reinforcement learning, one of the main differences that came in with the deep reinforcement learning.
Okay, thank you very much. We have about 2 minutes left, Susanne.
Yeah, I was going to address that. So originally we had scheduled 90 minutes. I don't know if people mind if we run like 50 minutes over maybe. I appreciate that some people might be pressed for time, but we have an audience of roughly 50 people. So I think we can maybe afford to run over slightly if that's okay with all panelists. Is that okay with all panelists? No objection, so maybe we can just proceed to the next two, and I wanted to add something after that as well.
Okay, Adam or Tom, would you like to say something? Adam?
No, I don't really have experience training this kind of multimodal systems, but I do have questions if after this topic.
Okay, Tom, do you have anything to add?
I think I want to just agree with my co-panelists. It seems like we don't have a very controversial panel today, but I think we're very much in agreement. I also see this question as like pointing to like learning the representation, if your input is fast, as being exactly coming in at the point where RL became deep, like this combination of deep learning, which was designed to initially work on image data, which is very, very large compared to some other data that was considered before. And a lot of the really good techniques from deep learning have been transferred into reinforcement learning world and have made it so that you can actually run reinforcement learning agents in worlds with large, multimodal, complicated observation streams, and then still do something sensible. One thing I want to push back a little bit against, just out of personal experience and experience seeing many of my colleagues fail, there's this very kind of neat idea of divide and conquer of like, oh, let's take the observation part, process it into a simple space, and then separately from that, take the simple space and do reinforcement learning, learn how to make the decisions from that onward. And many people have tried this. I have tried this myself many times, and many people have failed. And it's really, really difficult to get this right, because when you go from a large space to a simple space, if you don't have the guidance of what the task is, what the controllability is, what your action space is, if you just try to summarize a pixelated image, there's so many ways in which you could summarize it that are completely useless for acting, right? You could count all of the red pixels, or you could, I don't know, see if there's heart-shaped objects and so on. And those might not tell you whether you need to move left or right while you're driving. And so there's too many, there's too many possible mappings. And so I think trying to separate them completely is very difficult, maybe even doomed in principle. And what DeepRL did, what DQN did, was one of the first effective methods that actually did this end-to-end, where there was the same like gradient loss signal from the Q values, from the decisions themselves, all the way into the convolutional filters of the image processing. So the images were processed in a way to create better values for decision making directly, without an intermediate stage in between. And that, I think, was a very strong success. And I think we should not try to abandon this. We should try to complement it, because it's not always sufficient. Sometimes there's not enough reward signal. There's not enough to learn about the decisions to drive the full processing stream. It's probably very difficult to learn how to understand, say, language, if all you ever get is like a slap on your fingers when you give the wrong answer or something like that, right? So you may need additional things, but we should also try and keep them joined rather than try and separate them out again. That was the main point.
Splendid. Okay, Adam, you said you had some questions.
That's great.
Yeah,
can I just quickly jump in before Adam's question, because I suspect it's a question that's a little bit wider and more so. Is that right, Adam?
Yeah, I'm hoping it will be yes. More of a question which we can disagree on.
So as we're approaching 12 o'clock and the deadline to expand this maybe slightly, I just wanted to mention that the question in itself, and linking back to the notion of equality, is actually quite, well, if we go a male cliche, quite a cliche male question, exploration and to the limits and, infinity and beyond sort of approaches. So, from a female perspective, I was wondering about the definition of the word completely as well. It's implied in the question that if the world wasn't vast, it would be explorable completely. And so there's a question, how do you define completely, even in a very small, very limited world? But that might be a side question. It might not be relevant to the debate. I don't know if anybody wants to say something about this. If not, then I would lead on to Adam's question.
Alex, take it away.
Yeah, I think it's a really interesting point, because I think that, in fact, you could find, I don't know, I'm sure there's some quote about infinity in a drop of water or whatever. I mean, it's kind of, and I think especially when it comes to exploring consequences of actions, and I think especially when you come into a social space as well, we think of, I mean, I've quoted exploring and reasoning within No Man's Sky. And I just noticed the how gendered that was. But if you were to imagine trying to reason and learn within a social space where we're thinking about the relationships between people, maybe thinking about a theory of mind and understanding what somebody might be feeling based on what they might know. So I did some work recently when I was at Bossa using planning and limited knowledge, because you can generate really interesting stories if you assume that your agents have an incomplete view of the world and will reason from that. So for instance, Romeo is not going to kill himself unless he believes Juliet is dead. And Juliet is then, going to come back to life and realize that Romeo has died, has killed himself, and then she will kill herself in turn. So you build interesting narratives from incomplete and incorrect knowledge, and representing that is kind of really interesting and important within the game space. So yes, I agree. Thinking of this as a physical exploration of a limitless world really does constrain the discussion, and we should maybe think about infinite possibilities within a finite space as well.
Good point. Thank you. Anyone else? Then maybe over to Adam, to your question.
Thanks. Yeah, so like current reinforcement learning systems, usually you train them for a day or for a week or even for a month, and eventually they reach a performance where they don't improve anymore too much. So the question is like, what do we need for a system which worth running for example, a billion years in like current computation? So a billion years of current level computation, that's a lot of computation, but it's far from infinite. So it's really, you cannot be wasteful still. It's an immense amount. But the question is our current algorithms good enough to keep improving for a billion years if the environment allows that complexity? Or do we need a new algorithm for that?
Even waiting for a day could make a massive difference to the outcome. Okay, so maybe Tom.
Okay. As having been involved in one of these many years of compute projects that was AlphaStar, I'm not sure, actually. I'm not sure if we were to just run things for a billion years, if they would still keep going. In many of these rich environments, like the game of Go, like StarCraft, the curves still go up. Like we stop at some point because we run out of patience or run out of compute budget. And it's not that we stop because they have finished, because if the environment is rich and if there are always more things to find, then it's just the compute that is the limit. So in a sense, it could be that you could run these for a billion years and they would keep getting better. But my hunch is that they would keep getting better at extremely diminishing returns, so that the curve kind of flattens and flattens and flattens. And so you really don't get much out of the last 999 million years. And that's not what you want, right? You do want something that's kind of, like it has some kind of good progress curve. Ideally, it builds up skills and accelerates, right? The more you've learned, the easier it is to learn the next things, which is what you would expect from maybe a human expert who's maybe having a hard time learning the initial first skills, but then really takes off after they've built up their skill set or their like after they're capable of exploiting the many affordances that the environment gives them. So, and I think for that kind of learning, we don't have the algorithms. I think the current algorithms aren't designed to be open-ended because we've inherited so much from supervised learning, which goes to a fixed point, which is trying to converge to a specific point rather than to keep going up forever. And it's inherited too much mental baggage from gradient descent-based ideas, which just take these small steps. And the longer you run these, the smaller these gradient steps become naturally, because you can't keep making the same amount of progress if you're just following gradients. So you need jumpier things like what we talked about, the evolutionary ideas before. Those have a chance. But I don't think any of us have a really good candidate algorithm that they would bet on and say, like, okay, I've seen, say, the learning curve for the first 0.1%, and I'm going to extrapolate that this one is going to keep up at this rate and this one is going to keep up. I don't think any of us know those yet, but it's going to come up more and more will be running more and more challenging tasks. And so we'll be throwing more and more compute at the tasks because we care about solving them. So we'll have to find the algorithms, but I don't think we have any.
Okay, I think we have time for one more answer on this one. There is a question from Francesco to, I think, Guy. I would suggest, because Guy will be on panels more regularly, that we actually defer this question to the next session, if that's okay with everybody else, and to maybe make the most time of our current one time of panelists, if that's okay. Anybody else who wants to take that question?
I have a quick point to make about this question, because we always think about computational powers and running for billions and billions a year. Like, this is a common topic. But I think what is missed, I think what we should discuss a little bit more is representability. Because if you take a linear model to learn a value function, like, you can run it for like a billions of years and nothing will happen. Like, you cannot learn more than your model can represent. So I think maybe we can think about this computational problem more from a representation perspective. Like, the definition of representability of a model is that the model can represent perfectly the phenomenon. So if you're learning a linear system and you use a linear model, then you have realizability because you are using the right model for the right phenomenon. Whereas for this kind of environment like Go or StarCraft, representability is a little bit harder because you need to represent a phenomenon which is highly nonlinear, which is highly multimodal, which has a very complex loss landscape. So I think what we should focus also to discuss is how to represent the knowledge, how to use our inductive biases to represent the knowledge. For example, there was a recent paper about the inductive biases of deep learning. And for example, these are to use convolutional networks instead of multi-layer perceptron when dealing with images, or using transformers, graph neural networks. So there are many different models, and maybe we can reason about the representability and how the computational levels that you require an agent to learn with the realizability of each model.
Okay, Alex, just quickly, maybe.
Sure. I guess one observation I would make is that, we know that there is a certain type of compute engine that is able to wrestle with these kind of problems, and that's the human mind. And, therefore, we know it's a solvable problem. So I wonder if, we can we don't need to worry about billions of years of compute cycles on a simplistic algorithm, but maybe, assemble a more complex algorithm in a shorter time. That would be more fun and more attractive. But I don't have a lot to say on that, I'm afraid, Susan.
Oh, that's fine. It ties a little bit in with what's completely is what can be defined by us humans. And basically, we're asking a machine to go beyond that limit. And what use is that limit if we cannot then understand the feedback because it exceeds our own capabilities, if that makes sense. So maybe there's also a question how useful it actually is to try and do that task. Okay, so I think I would like to wrap up today's session. First of all, thank you so much for the panel. It was really, really great. This was our first seminar in hopefully what's going to become a monthly series, aiming at taking place on Wednesdays or Fridays each month. Thank you also for the audience. I'm actually quite happy that so many participated. I was sending out emails, but I wasn't sure, whether they were received. And so thank you so much. Sorry for those who had questions that couldn't be discussed today. There will be more opportunities hopefully to come. I would like to draw your attention to the conference, the iGGi conference. So if you could please put the 8th and 9th of September this year into your diaries. iGGi will have an internal day on the 7th, but the conference is open it had to be cancelled last year, but it's open to essentially industry and everybody who wants to join. Essentially, you have to register, but it's open to the public essentially, and it would be great to have as many people on board as possible. And obviously, games industry is a big part of that, where students, iGGi students, basically showcase their work. It's going to take place on GatherTown this year, and yeah, what else to say? Thank you so much, and hopefully see you again soon if anybody else has a comment. Also, thank you, Guy, for being such a cool co-moderator. I think we could become a regular team, no?
I love the idea that we're being moderated by Guy's floating head. It
It's very effective. I feel like Holly from Red Dwarf.
Yes, that's right.
Okay, so I think we call it a day. Thank you, everyone, again. And
thank you very much.
Thank you.
Thank you, everyone. Take care, everybody.
Bye-bye.
Thank you. Ciao.
Thanks, folks.
Thank you.
Bye-bye.
Ciao.